Hey robot makers, do you want to learn how to build your own custom machine learning model that can do object detection using Python and PyTorch? Then this is the show for you. So let's dive straight in. My name is Kevin. Come with me as we build robots, bring them to life with code, and have a whole load of fun along the way. Cool, let's get over to our keynote and make a bit of a start. So why is C3PO or C2PIO saying YOLO? Anybody got any idea what that's all about? We'll get into that in a second. So the process of building your own machine learning model, I'd say it's pretty straightforward. There's a number of different steps that we need to go through. Some are more simpler than others. So the very first one is to collect a whole bunch of images. So what I want to do today, I want to build a machine learning model that can detect different types of microcontrollers. So I've got a couple of microcontrollers here, for example, with the Raspberry Pi Pico 2 there. We also have a BBC microbit there as well. So what I want to be able to do is take a whole bunch of pictures, lots of different angles, lots of different lighting scenarios, different surfaces from different angles, as I've said. The more the better. We need at least 100 images per each object that we want to detect. So that's kind of what I'm aiming for. I've also got a ESP32 camera there as well that I'm going to include in the model. So I did spend most of Saturday taking lots of pictures and then doing the next step, which is labeling the images. I'll show you how to do that in a couple of seconds time when we get into the demo. It's quite a fun thing to do. It does get a little bit laborious after a while, but that's how we actually build up the assets that we're going to use to train our model. The next step then is to split those images that you've labeled and you've taken. You're going to split the folder that's got all that information in into two parts. You're going to create two folders. We're going to create a train set and we're going to create a test set. So the train set is what we use, the data set. All those images are going to go into the model to be trained on, and it will never see the ones that are in the test set. They're going to be used to make sure that our model is working properly, and we can evaluate it against that to see how well it can detect an object on an image it's never seen before. Once we've done that training of the model, we can then evaluate it. There's lots of different stats and graphs and things that PyTorch, which we'll be using today, gives us to evaluate this. And you can see where there's particular models might need a few more pictures taken, some different scenes that you might want to put them in to get the graphs to be where you want them to be. Then we'll deploy the model. And what I was hoping to do today was I was hoping to deploy one of the models onto the new Raspberry Pi AI camera. I've got set up next to me, and it turned out to be a lot harder than I expected. In fact, I wasn't actually able to get this running, and there's a number of reasons why. We'll get to that towards the end of the show, but I'm hoping to follow this up with another video where I'll show you how to compress, quantize and load this onto the Raspberry Pi AI camera. But we can use the model that we created today. I'll give you a demo of that and we can see how well that goes. So first thing we need to do, here's a bunch of BBC microbits that are on my desk, and you can see there I've taken them from lots of different angles, lots of different camera, focal lengths, things like that, different lighting conditions. These ones have all got the same background on the same desk, so I need to take them and put them in different places to supplement that and make the model even better. So the more that you can take, the better. You need at least aim for 100 images of each object. Use different cameras, different focal lengths, different lighting conditions. I found when I was testing this in low light, it didn't really work very well, so I'll need to take some more samples in lower light. And different focal lengths, different cameras will also give you a better model as well. And we're not looking for like 4K images either. We're actually going to squash these images down to quite a small size. And the actual colour isn't that important either. It's more to do with just the objects and the detail that makes up that object for us to capture that. And don't forget, if you're taking a picture of loads of BBC microbits, for example, you might want to flip it around and take pictures of that side, maybe edge on, maybe some extreme kind of angles. The more angles you've got, the better, the more able the camera, the model that we're building will be able to detect this in any scene that it comes across. So that's collecting our images, that's a load of fun. The next bit, which is annotation, labeling the images, we can use some software like Label Image. This is available through pip. You can do pip install label image and it will install this particular software. We'll have a look at this, like I said, in a minute or two. And we're going to label the objects, and you simply do that by clicking and dragging a rectangle. I think you press W to make it into rectangle mode. You draw a rectangle around the object. They're not all nice and square on either, so sometimes you have to draw a rectangle quite, the bounds are quite outside of where you would think it to be because it's kind of at an angle, but that's what we need to do. And then a little pop-up window will appear and we can then name the object. There's a list of things that we can name the object from. We can have as many of these as we like. I think the mobile SSD model has over 1,000 different classifications, so we can certainly have at it with all the different microcontrollers we want to train this on. You can see there it comes kind of preloaded with a couple of examples: dog, person, cat, TV, car, meatballs, marinara sauce. Completely random. I also get added to the end of that, and it's quite intelligent. This, if you like press a key, it'll auto complete what it thinks that could be and drop down if there's multiple options for that. So you get into kind of a flow with this, and you can have multiple images, multiple objects in one image, and you can draw as many rectangles as you like around them and have them labeled individually. It's quite clever in that it can do that. So what it will then do is it will, when you click save, it will save either as a Pascal format, or it will save as a YOLO format, and I think there's another one. We want the YOLO, you only look once format. That will create a text file, a .txt file with the same name as the image that you've loaded in, and in there it will have a couple of things. It will have a number, and that's a number from that list you can see on the right hand side there. That's the class number, so it doesn't have the class name itself, just like a number representing that. And then it'll have an X, Y, and a width and a height as well, but they're expressed in a sort of normalized way, so they're a value between 0 and 1, and that's because if you bring in a really large, I'm making my arms large here, if you bring in like a really large image, you want it to be able to scale that bounding box wherever it is. So depends on the size of the image. This doesn't care about that because it's normalizing that height and width. Just give that a second to catch up. So we just had a bit of a second there where the stream was catching up with me. Okay, so next up then we have splitting the images. So we have a special function that we can use in PyTorch for actually splitting the image set, and in that image set is essentially a folder with images in it and the labels for each one of those images. We can split them into the training and the test, and we can do that in a kind of proportion, like 80-20 ratio. So 80% for the training, 20% for the test, because we want as much as we can to go in that training model, but we also want to keep some back that it's never seen before to show how well the model is actually working. So once we've done the splitting of the images, then it's time to get in to train the model itself. So this is the funnest bit and the bit that takes the longest time to do, depending on what kind of hardware you've got. So we're going to be using a library in Python that's called PyTorch. I think this is a Google or Meta created one. I can't remember who created that, but it's one of the big companies anyway that have created this. And we're also going to use Jupyter Notebook. This is really good for working with different data sets, and you can essentially rewind and play back different steps of your code, which is really cool. So if you're testing things out, things don't quite work the way you expect, you can just update the code, run it again. It'll carry on as if it's run the entire code up to that point, which is really neat. We'll have a look at that as well on the demo. So to install Jupyter Lab, you simply do pip install Jupyter Lab and then just type Jupyter Lab correctly. I think I've got a typo there on my slide to launch that. Now the training itself can take a couple of hours to do. I ran 50 epochs, 50 cycles of training, and that took an hour on my Mac M1, which is Apple Silicon. And I was also using the Apple Silicon MPS, which is like the accelerator that's built into Apple's. If you did that just on the pure CPU, I think it would take a bit longer. If you've got like an NVIDIA, you can also use that as well. So there's different options for speeding this up a little bit, but it will take a while to do. Once we have the model built, we can then look at a couple of graphs. You can see there that confidence curve. You can see there's a couple that it's not very confident about. So the the Arduino Nano Every, I only took a couple of pictures of that, so it's not very sure about that one. Whereas the ones that I've got the most on there, the Microbit, it really is confident it can detect those. And then there's a couple of other graphs there, and you can also see on the right hand side where it's detected various different things. It's put a little bounding box around it, and it's given it a label as well. So that's it detecting these things based on the training. And then once we've done that, we can deploy the model. So we end up with a file that we can copy and paste onto other devices. We can share that with other people, and these are quite small, about 30-40 meg when I created this one. They can be even smaller once we quantize and compress them, and we'll get into what that looks like in a minute or two. So, in fact, here we are now. So, compressing and quantizing. So, compressing is where we will look through our model, and our model is like a tree, it has lots of different branches on it, each representing a different feature of the machine learning model. And sometimes we can squeeze these two together, we can fuse them together, and essentially they become one layer rather than 2 or 3 different layers. It's an operation that we have to have the computer do itself. I don't think you'll be able to do this manually. And in doing that, you can make the model smaller, quicker to process, but you can also lose some of the quality, the granularity of your model. So it depends what you're going for there. Quantizing is where we take the actual values that are stored in the model. The model is essentially just a whole bunch of weights, and these weights are stored as 32-bit floating point numbers, so they're very large numbers. And what we want to do is squash them down into an 8-bit number. So if you think about your microcontrollers, if I pick up this microcontroller here, for example, this has got a 32-bit processor on it. If I grab the Arduino Uno clone that I've got here, this is an 8-bit processor. So this is like, 4 times more capable from a processing perspective than this Arduino Nano. And essentially what we want to do with our model is make it work on really small, less capable devices. So by making it 8-bit integers, that means that our model will be significantly smaller, and we can do that with this quantizing where we don't actually lose a lot of quality. It's surprising how well the model will work with that lack of granularity there. So that's the compressing, and here's the quantizing. So yeah, it reduces the precision of the model's weights, typically from this 32-bit floating point to 8-bit, reduces the size, the memory footprint, which is really important when we're looking at things like that AI camera, which has only got a couple of meg of onboard RAM. So it means that the model can fit entirely in the memory, and it also means that it runs more efficiently on hardware with limited resources. So you can run, I understand, some models on an Arduino Uno with this 8-bit processor. Not these particular machine learning models with cameras, I'm talking